Do you guys remember who came up with the notation on the left? It's that German guy.
Didn't it start with a T?
Starts with an L.
No.
Larry is close in that it does start with an L. Leibniz is his last name. Gottfried Wilhelm Leibniz. Okay.
Are you supposed to be holding that piece of numbers?
Who came up with the other one? F prime.
What a guy.
English guy. Just take a guess. Famous math science guy.
Isaac Newton.
Newton. There you go. Leibniz came up with the notation on the left, the dy dx. Newton came up with the, more or less, with the F prime notation. So let's just follow the instructions. The instructions say multiply both sides by dx. So if I were to do that, I get dx times that side, dx times that side. What happens on the left side if you treat that like a fraction? Yeah, the dx's do what?
Cancel.
Yep. So I end up with dy is equal to f prime of x times, we don't often write the times, a lot of times we'll just write dx. So dy is the differential of y, and dx is the differential of x. What does that mean, really? Differential of y means like a little tiny change in y. Dx means a little tiny change in x. And that's it. Okay, so your process is really simple. You find a derivative, and you just multiply the dx over. That'll give you your differential, which most often referred to as dy. Okay? So the question naturally, I mentioned this earlier, but I'll say it again. The question naturally is like, why would I do that? Who cares? It leads us right into what an antiderivative does, which you saw in the video a little bit last night. It also leads us into another question about what about the dx, and where does the dx go? Maybe you already had that question. We'll see. Let's do one example here and just kind of see what these could look like, and then we'll move on. So we'll skip the spherical balloon. There's some really interesting approximation things here, but we'll just do number one. So for number one, if you're trying to find the differential, here are your steps. Step one, find dy dx. What would that be using the power rule? 2x to the negative 1/3. That's our derivative. That's our dy dx. If I want the differential, I multiply both sides by dx, causing the left side to get a good cancellation where the dx's go bye-bye. I get dy equals 2x to the negative 1/3 times dx, or just dx. And that would be my differential. It's dy. Okay?
This is not finding the derivative. This is something different.
It's finding the differential. We're finding the itty-bitty change in y.
Could you expand on that?
Very briefly. So I'll come back over here and rewrite the derivative. Dy dx equals 2x to the negative 1/3. So what this is, I'll try to show you a graphical representation. On a graph of y, would you agree with me that dy dx is the slope of y?
Yes.
So dy dx would represent the slope along that graph, right?
Yes.
Okay. So then if I go to my differential, dy equals that. This is essentially saying change in y equals slope times change in x. Do you agree? Change in y equals slope times change in x. In other words, if you've got a slope, you know what that slope is, in this case 2x negative 1/3, then how much the y changes depends only on how much the x changes. Right? So I'd say if my x goes from here to here, this would be my dx, and then my dy would be represented by that. But if I maintain the same slope, and then my dx goes from here over to here, that's obviously going to produce, that new dx will obviously produce a much larger change in y.
So if your slopes go on the x a value 2, your dy is 1.
dy is 1. But if you went 10, your dy would be 5. Make sense?
Yes.
So we're just finding what is the vertical change based on slope and horizontal change. So it's a way we can approximate a value of a curve
For a different point.
or the value of a different point. Right.
Is that as complete as we need to make it, though? We don't actually have to find what dx is?
Nope, like
No. So that should
if
be
you are asked to find dy, the thing in the blue box is it.
awesome.
Yep. Okay, cool. All right, so let's do a little switcheroo. Let's take a look here at 4. And I wanted to do some reviewing. I don't often do this with videos, but I wanted to do a little reviewing. And I want to be open to questions from you guys too. So I'm really hoping y'all nailed the video. I'll check that, I don't know, maybe sometime this afternoon. But I want to make sure that we're off to as great of a start as we can be with chapter 4. So let me just quiz you a little bit, see how much you remember. Can anybody tell me what the function inside an antiderivative is called? It's an integrand. Yep. So integrand is spelled like so. And that's the expression that we're finding the antiderivative of. If you haven't watched the video, this is the skeleton version of it. You'll want to watch the video. I skipped some good stuff already. And then as you do your antiderivative and you come up with this new function, in this case it's noted with a capital F of x. What do we call that capital F of x? That's the antiderivative. So what that is, let's try that again. Derivative. So what that antiderivative is, it's the function that if you differentiated it, you'd get the original integrand. Right, because we're doing the opposite of a derivative. So you should be able to check your answer by doing a derivative on your answer and see if you get the original expression. Does that make sense? And then lastly, for me, on this at least, what about this? That's a constant. We call it the constant of integration. Why on earth does it have to be there? Because I don't want you to make any mistake about this. It's not an option. It has to be there. Why does it have to be there? Could be any, not anything, any constant, any number, right? Any constant, it could be. And why could that be there? Why does that have to be recognized?
Derivative of a constant is 0.
That's right. So I should be able to check my answer by differentiating that antiderivative. And a plus c representing some unknown constant. Well, the derivative of any of those would just be 0. So c could be any constant, really. Okay.
So if the constant can be any number, then couldn't it also be 0?
Sure could. But if you put plus 0, what are you telling me?
That there is a constant.
And it's
0.
0.
Okay.
So you better be sure of that, right? So you put a plus c there to say, hey, it could be 0, or it could be 10/3, or 74 pi divided by the square root of 111. Who knows? It could be anything. Any constant is what the c represents. Okay. So any questions on naming stuff? The other names are in there, and if you watched the video, hopefully you saw the whole little thing about why the c at the start. Any follow-ups or questions? Please do ask. Don't be shy. Oh, we'll keep going here. Oh yeah, go ahead.
I was just a little curious when you have dx at the end of all of these, and then it kind of goes away.
It disappears.
And how do you know? Like even when it's like when they're added together, when it's a product or sum. If you don't do dx and dx, it's just dx kind of just hangs on at the end.
Sure. Well, it depends on how you define it.
Okay.
I'll do it. Hey, so I'll address one of your questions. Do you guys remember these? Yes, Robbie. We'll start talking about area tomorrow. This leads us to yeah. You guys remember these?
Yes.
So remember when we did the derivative of a composite? We used the chain rule, right? Remember how the boxes illustrated that? So check this out. It's a good connection. So remember how symbolically when I open the box I'm doing the derivative, right? So I'm doing the derivative of the outside function. And I look in here and so I look in here and there's another box, right? And so I take this box out and I say, all right, let's differentiate this. Open it up. Now I've differentiated that one. And then finally I get to my innermost function, right? So that's when we were doing a derivative of a composite. And do you guys remember how at some point in there I mentioned, and it was kind of hard to grasp at first. Remember how I told you we've always been doing the chain rule, you just didn't know it? So here we're going to kind of reverse that. So if doing a derivative of a composite leads us to unpackage all these boxes, wouldn't an antiderivative be the reverse of that? Wouldn't an antiderivative basically be repacking the boxes? So think of this as your dx. I'm just going to put it back where it came from. And then put it back where it came from. So right now, so we're going to get into some more details when we get to section 4.5. But right now, you look at it and you think to yourself, the dx, like in all those examples you saw in the video, just seems like it disappeared. Where is it going? Well, the truth is, we'll be able to see this a little bit better when we get to 4.5. The truth is, it came from doing a chain rule, so we're just going to put it back inside. It's not really disappearing, it's just going back into the input. And that's why it seems to disappear. Because right now, you can't see the Santa anymore, right? Somebody will be like, where did Santa go? I'm like, it's in there. Hear it? A little bit of rattling, a little bit of extra jelly beans rattling in there. He's in there, but you can't see it. So the dx just goes back into the input. You can't really see it, but it's there. Okay? Good question. Yes, sir, K-Bar.
Are integral and antiderivative same?
So an indefinite integral and an antiderivative, same thing. And of course, if there's an indefinite integral, it begs the question, is there a definite integral? And there is. So I'll use them pretty interchangeably. When we get to section like 4.3, we'll start to look at what we call definite integrals, and that's where we make a really great connection to area, in conjunction with tomorrow and later on. But for now, we're essentially answering this question: what is the function that if I differentiated it, I'd get the integrand? Like we're just reversing derivatives right now. Okay. Let's look at a few rules here really quick. I know this was in the video, but I think these are worth going over again. Did you all notice that the left-hand column should look really familiar to you? Like the derivative of a constant is 0. And down there at the bottom is the regular old power rule that we learned, right? And then you keep going, and there's all these. It doesn't have the product and the quotient rule yet because we don't have a nice corresponding rule for antiderivatives at this stage of the game, but it's got all your trig derivatives. And then I'm sure you noticed on the right-hand side, these are all just basically the reverse, right? They're all antiderivatives. So the antiderivative of 0 is just 0 plus some unknown constant, right? So I wanted to focus on a couple of these right here and let you know what they are and what they aren't. So the first one there I just mentioned. The second one I think is definitely worth discussing briefly. I think I did this in the video, but I want to do it again. I want to make sure we have every chance to get off to a great start here. K just stands for some constant, right? So if we had the integral or the antiderivative of 3 dx, anybody want to take a shot at what you think that would end up being? 3x plus c. There you go. If it's the antiderivative of 12 dx, what do you think we'd get? 12x plus c. So that's why they feel comfortable saying, all right, it's the antiderivative of k dx. You just get kx plus c. And again, because you guys have gotten really good at derivative rules, especially the power rule, like we're really, really, really good at that, right? Stuff like this, you should be able to just differentiate it really quick and check your answer. You're like, oh, yep, it works, it matches, we're good. The next one, did you notice how the k migrated? The k was in there as part of the integrand, and then all of a sudden it's not. That's because it's a constant multiple. And just like with derivatives, you are allowed to take a constant multiple, not a constant term. You can take a constant multiple out, do whatever you got to do with the antiderivative stuff, and then multiply it back in when you're done. Just like we do with derivatives sometimes. Here on this next one, did you notice that it's the antiderivative of a sum or a difference? What that means is you can do the antiderivative of the first term plus or minus the antiderivative of the second term. In other words, you can go term by term by term by term. Sometimes a very useful rule. Can I tell you what this is not? I want to be super careful with this. That principle works for plus and minus. It does not work for products. You watching? Check this out. If I had the antiderivative of f of x times g of x, that is not equal to. Is that enough? That is not equal to this. Okay, so sometimes people will overextend that rule and be like, oh, okay, I'll just go term by term with a sum or a difference. No problem. Hey, I'll just go factor by factor with a product. Major problem. We'll learn how to deal with those later on. Okay? Can you imagine why I'm showing you that?
Because you know students.
People do it all the time. Right? Okay, cool. And then the last one, hope that you recognize this one. Isn't this just the reverse of the regular old power rule that we've used a million times? Think about that derivative power rule. Don't you, like for the derivative power rule, like you got x to the n, don't you bring the old exponent down in front? And then subtract to get the new exponent, subtract 1? Well, here, we don't do any subtracting, we do adding. Does that make sense? And instead of bringing the old exponent down in the front to be a coefficient, we actually bring the new exponent down below to be the bottom of a quotient. Make sense? Okay, I hope it does, that's just the reverse of our previously mastered power rule. Okay, any questions on any of that? Okay. Did anybody have any follow-up questions on any of the... I did a handful of examples in the video itself. Any questions on any of those? Like maybe you were following along and you got to like number 3 and you're like, oh, I thought it was going to be this and it was something else. I'm confused now. Anything like that at all? I'm going to give you a chance to ask and express your confusion or frustration or whatever. Say again? 6 and 7? Okay. 6 and 7. Okay, they're at the end. There we go. Okay, cool. So let's, this is worth, I think they're both real good. So, like a total rookie, total novice that thinks they know more than they actually do know would make some pretty egregious errors with these. Okay? So can I make those really ugly errors? You might have been tempted to do this yourself. And that's okay, because you're just beginning. Somebody might look at this and say, oh, okay, it's a fraction with a bunch of exponents and variables and stuff. Let's do this. By the way, this is not good. Don't do this. So this would be tempting. So somebody would be like, all right, let's just, do you see how I'm doing a bunch of power rules here? I'm just adding 1 to the old exponent and dividing by the new exponent. And down here, yeah. So I did it. Let's put a plus C on there and I'm done, right? So this is really, really, really bad. Because essentially what somebody's done here is they've said, hey, the integral of a fraction is equal to the integral of the top divided by the integral of the bottom, right? Essentially what I did. But you're going to find if you tried to check this by doing a derivative, you don't get anywhere near the original integrand. You're going to be way off. It's not even close. And so you're also going to find that the antiderivative of a fraction is problematic at best. In fact, over the course of our entire year, we are going to learn how to deal with only 4 different fractional forms. That's it. Only 4. Because the 5th and the 6th and the 7th are just different and we'd need more time to be able to process that. Only 4. So here'd be my advice to you right now. If you're doing the antiderivative of whatever and the whatever is a fraction, do whatever you got to do to make it not a fraction anymore. Okay? So in this case, I think the best way of doing that would be to flip the denominator up. So it'd be the numerator as is, and I am absolutely allowed to do this, right? Just move that denominator up and make the exponent change the sign. Yeah? Totally can do that. But then, do you guys remember a second ago how I told you that the antiderivative of a product, which is what this is not equal to the antiderivative of each of the factors? So a product is itself kind of an issue. What could I do to take this from being a product to being not a product? Say again? Yeah, what is it? Distributive, yeah, multiplying through the distributive property. Jake, you had the right kind of hand motion. You're like multiply it. Yeah, whatever. Okay, so then it ends up being the antiderivative of x to the 5th minus 6x to the 3rd plus 1 dx. And now I basically just have a sum and difference. I can go term by term, right? So I just use my power rule several times. I'd say the antiderivative of x to the 5th is 1/6 x to the 6th minus, it'd be 6/4 x to the 4th plus x, 1x, right, plus c. What do you think, Eddie? Meg? So Eddie, 7 is really no different. Honestly, God. What's that? Yeah, I would rewrite. I'd rewrite it as x plus 1 times x to the negative 1/2. I would distribute and go term by term. So I think 6 and 7 do look a bit different, but it's the same skill and concept leading up to it. Let's be honest, like most of the time you'd spend working on 6 and 7 has nothing to do with calculus. It's about algebra, right? Flip up, distribute, and then the calculus is like power rule, plus C done. So, yes, ma'am.
So this one we have like +1, right?
We're talking about 6?
Yeah.
Yeah.
But if it was, if it was like +5, would it be 5x?
Yep.
Would it be x plus 5?
Yep. Because you should be able to differentiate the thing you came up with and get the integrand. Like, so if it was +5, and I propose, okay, I think the antiderivative would be 5x, I should be able to differentiate the 5x and get the 5. And since we're already like really good at derivative rules, it's a pretty good check, right? Because if honestly, if I asked you on a quiz, like, hey guys, what's the derivative of 5x? Wouldn't you immediately suspect some kind of a trick? You'd be like, that's way too easy. Because you already know that so well. My point is you're really good at it. Use that as a way to check. I should throw that on there just to see if, like, your blood pressure rise. Like, he's really asking me the derivative of 5x? Something's wrong here. Can't be right. I'm kidding. I don't want to do that.
Ryan told us to please do that like in 2 times.
You're like,
I didn't hear.
old quiz of that, right? Yeah.
I didn't hear anything.
Fair enough. Okay. Any other follow-ups, questions?
Finding the constant.
We will today. You're talking about like how do we find actually what the constant is? We will do that at least once today. Yep, I'll show you that. Okay. So I want you guys to do a little practicing. If you guys would, take a look at numbers 9, 10, 11, 12, 13. Yes. Please try all of those. And I have a suspicion if you learned all you can from the video, you got a shot to make some decent progress. In a few minutes, I'll show you some answers, and then we can discuss as needed. Whatever. Rob?
To do like the opposite way, like rules, like what we usually do for like a quotient.
Oh, like a number 12?
Yeah.
So like I said before, we're going to find, like you can try stuff like that, but you're going to find pretty quickly that the antiderivative of a fraction is a lot trickier than the derivative of a fraction. And you can get yourself into some really, really difficult territory easily. And so because of that, if we do see that situation, we're going to try to avoid it. And be like, how could I turn this thing into something that's not a fraction? So for now, that's going to be my advice to you. Is that okay? Like pretty soon, like when we get into it'll be chapter 5, so it'll be early second semester. We'll start to get around to like okay, what if it's a fraction? What do we really do? And we'll look at several examples of what you could do, but not for now. We're just going to like do some flipping up and some dividing and do whatever we got to do to make it not a fraction anymore. Yeah. Others? Anybody? Okay, so can I let me ask Dan's question in light of number 10. Does number 10 seem like an appropriate one? Like the addition?
Not so much. I think it's just the question of the puzzle. I think that's...
Well, but this is a sum kind of like that, right?
Yeah.
So do you remember what the ed puzzle question was at the end?
I have it written down.
Because I'd be happy to address that specifically if you want. Sorry, hang on 1 second. Just do a little zooming. There we go. Okay, go ahead.
Antiderivative of 5x squared plus sine x dx.
Okay, so Dan, if I misspeak at all, you let me know, but I think this is what his question was. Dan said, hey, I'm comfortable with this, and let's make sure that you guys are comfortable with this also. Am I right? Okay, so Dan's like, hey, I'm comfortable with that. Are you guys comfortable with that too? If you got a sum or a difference, you can split it up into separate integrals, right? Okay. And then Dan also said, hey, I'm comfortable with this and comfortable with this, but I am not, right? But I am not comfortable with that, right? Okay, so here I think was Dan's question. I think it was something along these lines. Shouldn't there be a plus C here?
Yeah.
And shouldn't there be a plus C here?
Yeah.
Have I got this right? Okay. So I'll be straight up with you. Let's pretend that was some quiz question or test question, and you responded with my final line there as your answer. I would absolutely give you full credit. There is nothing at all wrong with what you've done. It's a little misled, and it's not the standard way of doing things, but it's certainly not wrong. Let me explain why this original answer is not only just as good, but because it's slightly less writing, certainly preferable, right? Let me explain why. This is a really wonderful question. This gets to the idea of what in the world is this plus C thing anyways? It stands for some unknown constant that could be added on to the end of any antiderivative, right? Because the derivative going backwards of that would be 0, right? So if C, this one over here, is really just some completely unknown constant, and this C is similarly some other unknown constant, what is some unknown constant plus some other unknown constant? Just some other one, right? Some other unknown constant, also known as C. So could it be this? Could it be this? What if somebody proposed, I just heard somebody say 2C, right? What if somebody decided, you know what, I think the answer should be blah, blah, blah plus 2C. Is that so wrong? Quiz or a test, I would definitely not mark any points off for that. Again, sort of awkward, but not bad in the sense that, is there any number that you couldn't get to by multiplying some other number by 2?
Negatives? That's a lie. I'm sorry.
Right? So isn't 2C just some other C? And so if you wanted to be like, hey, I think it's a 2C. Oh, wait, no. I think it's really just plus some other C. We're good.
But isn't 2C different than C? Like that's still the case.
C is some unknown constant, right?
Yeah.
And so, again, is there any constant you couldn't get to by multiplying 2 times some other constant? You can't. So what you're getting at is actually, furthermore here is a good question. When we get into later on into our year in chapter 6, we will start to discuss things like what you're bringing up, such as, is it possible for one constant to be importantly different from some other constant? And the answer is yes, and we'll deal with it then. For right now, we're just going to say, hey, you know what? Some random C plus some other random C just equals some other C. Later on, we'll go a little deeper. It's a great question. Any other questions on the material? Okay, so then let's do a little bit of work. We're gonna finish our class by finding out, hey, under what circumstances could we actually figure out what the C is? And we'll go over a few pointers on quizzes and tests and stuff like that. Okay, so if you guys would take a look there on the left, would you guys agree with me that it looks like before you showed up to class, somebody did some sort of a derivative and they came up with that? Fair enough? Somebody did the derivative on something and they came up with dy dx equals 3x squared minus 1. When we are asked to find the solution to a differential equation, and that's what that is. If you're filling in blanks down below, a differential equation is an equation with one or more derivatives. And if you're asked to solve a differential equation like this, here's what they're really asking you to do. They're saying, find a function or find an equation like this where if you differentiated it, you'd get that derivative. In other words, go backwards and let's find the function that whoever did the derivative, let's find the function they did the derivative on. We're going backwards, right? It's like a little puzzle we're going to try to put together. I want to show you a couple of steps. We'll do another one of these just like this here in a second. I want to show you and make a little connection back to chapter 3. If I was going to try to find the solution to that differential equation, first thing I would do is I would multiply both sides by dx. I would get to my differentials. And like we did a few minutes ago, do you all see how the dx's would cancel? We'd end up with this lovely expression, this lovely equation, dy equals 3x squared minus 1 times dx. All right, so then the next question down there in the fill in the blanks, how do you undo a derivative, or more specifically here, how do you undo a differential? An antiderivative. Yeah, there you go. So an antiderivative, which is that tall, skinny s thing, An antiderivative is the way that you undo the differential. So I'm going to put that in. I'm going to say, all right, antiderivative of the left side. And of course, with an equation, whatever you do to one side, you got to do the same thing to the other side. So you're going to do the antiderivative of both sides. What would you guys guess the antiderivative of dy is? It would just be y, right? Because the antiderivative undoes the differential. You just get y. And then on the right side, I hope this looks pretty familiar. What's the antiderivative of 3x squared? X cubed. There you go. And the antiderivative of minus 1? Minus x. And then don't forget the plus c. And this would be a classic point where Sam asked this earlier. Hey, what about the dx? Where did it go? For now, let's just think of it as a repacking of those chain rule boxes. It just went back in to your input. Went back in to the x's. Okay. So if an initial condition is not given, this is blanks again, the answer will be a general solution. General solution with a plus c. So a plus c means you got a general solution. However, if an initial condition is given, the answer will be what we call a particular solution. The graphs over there to the right are meant to illustrate this. So if you would look, do you guys see how our solution curve was a cubic? Y equals x cubed minus x plus c. And do you see how all the graphs on the right there represent cubics? So what that is trying to help us understand is our solution curve would be this orange one if c equaled 4. If we had an initial condition that gave us c equals 4. If the initial condition led us to c being negative 2, then it would be this other graph that I've just highlighted. So really the solution curve could be any of those, and we really don't know which one it is unless we know information to help us find c. So it would just be a family of graphs would be our solution curves, unless we have information to find c, and then we could say, and it's that one right there. Help us pick it up, which is what we're going to do next, but first, do you have any questions? Okay, so do you guys love it when teachers are ultra clear with you about what's expected on quizzes and tests? I'm about to do that, so make sure you're paying really close attention. So take a look at this example here. This will be what we finish with. I think I will help you fill in the blanks on the next little piece, but we'll mostly be done with stuff at this point. Okay, so it says, example. Please look carefully at the wording here. We'll practice this a ton this year. This will be our first shot. It says, find the general solution and the particular solution to that differential equation, dy dx equals 1 over x squared, that satisfies the initial condition y of 1 equals 0. Okay, so guys, what we're going to do here is we're going to actually get to find the solution curve, and we're going to find the c. We're going to find all of it. This first step is really important. This is the part of me being ultra clear about what I expect. I'm going to rewrite the differential equation over here. dy dx equals 1 over x squared. This is why we started off with differentials to start our class off today. This is why this is, at least for your immediate future, at least bottom line for your grade, that's why this is really important. Your first step must be to show separation of variables. You see how there's y's and x's up there? On the left side, there's a y and an x. On the right side, there's only an x, right? Our first step is to algebraically separate them so that on the left side is only y's, maybe, and on the right side is only x's. No mixing on either side. So do you guys see maybe a way to do that? Yeah, multiply both sides by dx. This one is really a pretty simplistic version of that. So I'm going to multiply both sides by dx. The dx's cancel. I end up with dy equals 1 over x squared dx. This is where I'm going to be ultra clear. If that step that I just wrote is not written on your paper, I don't care what comes next. You will get no points. So the doorway for you to get any points on a question like this where you're finding a solution to a differential equation, the doorway that you must walk through to get anything is that one right there. You must show the separation of variables. I don't want you just to think it, or just to say it, or just to imagine it. You must write it. This gets to the heart of what an antiderivative actually does. And this would be the same kind of judgment, same kind of basis for judgment would be used on an AP test as well. I've graded many of these in which someone gets the right answer, like legitimately, like they get the right solution curve, but they neglected to show any separation of variables. And most years, they get nothing. Every now and then, they'll like find a way, like, oh, we should still give them a point or two, but whatever. They definitely don't get full credit. Most of the time, it's 0. Okay? So you must show that step. And you got to admit, if the rules are clearly spelled out for you beforehand, there's no excuse, right? I mean, we're all humans. We make mistakes. But you can't say, but wait, you never told me. I'll tell you this probably conservatively 50 more times. Maybe 60, 70, I don't know, a lot of times. Go ahead real quick.
So you have to show that you're multiplying both sides by dx. You can't just go to the next one.
No, you really don't. No, you don't have to show, like if you just, like here, I'll just illustrate your question. Like if you looked, I am erasing all my work there. If you looked at this and you thought, oh, this is that one where I got to show separation of variables. And the first step was you like mentally doing the whole multiplying and you just come up with this. This is what you write down. Full credit. I don't need to see the fact that you, I know that you know how to multiply both sides by things.
Okay.
So I don't need to see that. I just need to see the end result is that the variables were separated. Or better yet, what if you separated the variables in your mind and then you flipped the x squared up and instead of writing that, you wrote this? I think this would be even better. Do you see how the variables are separated? Do you see how the variables are separated? And do you see how it's ready to do an antiderivative? Because no longer do we have a fraction in there. Either one of those would be fine for this first point, showing the separation of variables. I think the second one's better because now we're ready to actually do an antiderivative.
Is it the dx x squared? Or is it?
No.
No, it's not.
dx is just dx.
So there's no number with dx? Or?
No, it's the differential in x. It's a little tiny change in x.
Okay.
Goes back to what Sam asked about at the start. Okay, so once you've done this, how do you undo a differential? We just talked about this. Antiderivative, that's right. So we get the tall, skinny s's in there. The antiderivative of dy is y. What do you guys think the antiderivative of x to the negative 2 dx would be? There you go. Negative x to the negative 1. Don't forget the plus c. Yeah, get that power rule solid. Okay, so guys, that is what we call a general solution. How do I know? Got the plus c. Right? If it's got a plus c, we call it a general solution. Here is where we can actually find the c. I'm going to use my initial condition, y of 1 equals 0. Are you guys okay with that being like function notation, like f of 1 equals 0? So in other words, when x is 1, the output, or the y, is 0. So I'm going to write that in. I'm going to say, all right, well, y is 0 when x is 1. See how I've replaced the y with a 0 and the x with a 1? I know that's true because I'm told that that's a point that's on my curve. It's actually really easy to solve for c now, isn't it? So you end up with 1 equals c. And then to write your particular solution, you would just rewrite your general solution, except instead of having a c, we put what the c is. It's plus 1. So this would be my particular solution. This would be my general solution.
Did you want us to label that?
No.
Sorry.
Go ahead.
How do you get c equals 1 from what they give you the y?
So this notation means one specific thing. It means when x is 1, y is 0. And so what I did is I replaced the y with the 0 and the x with the 1.
Okay, I see.
Anybody else? Okay, this won't take very long. Let's see if we can fill in these blanks. This will literally take us 20 seconds because most of this is review. This will lead us nicely into tomorrow. The derivative of a position function is a velocity function, all right? And the derivative of a velocity function is an acceleration function. And so if an antiderivative really is the reversal of a derivative, then the antiderivative of an acceleration function, velocity function, and the antiderivative of a velocity function, position function. That's right. So tomorrow, We will look at that, and if you've been in physics, tomorrow kinematics will all of a sudden make more sense than they made before. Seriously. Have a great day.